Okay, so welcome, and I'm very happy that you are interested in this talk. It is not my specialty, what I'm going to talk about. I'm mainly working in group theory, so at the end of the talk I will bend a bit of the problem and try to find some group theoretic analog of the problem. But first of all, let's play a little game. So there is this map of this very little town, and the leadership of the town is very smart, so they decided, first of all, that they need, of course, in the center, they need some pedestrian streets, so these are not, you are not allowed to drive on those streets, and also all streets are one-way streets, so it is somehow directed, as you can see on your map. So at certain points, you have a choice which way to go. There are two streets going out from this point, and you have to choose whether you go to the right or to the left. I mean right and left in the point of view of the driver. So this is right and this is left. Here also you have a choice. This is right and this is left. Here you have a choice. This is right, left. Here you have a choice, right, left. And finally here you have a choice, right or left. Okay? And the driver does this, that you place your start somewhere, go to the first intersection where you have a choice, and then I will tell you what to do. To go to the right side, and here you don't have a choice, so you go to the next crossing where you have a choice again. And then I say left, then you go this way. Okay? Is it understood? Is it clear? All right, so you start at any point on the map. You put your coin wherever place you want to start. It's up to you totally. And I will give you the instructions how to drive in this very small town. So you put it somewhere, and then you have to choose, and the first choice is to go to the left. The next intersection. Then go to the right. Then go to the left. Then again to the left. And then to the right. And then to the left. And then again to the left. Where are you? At CEU. All of you are at CEU. Independently where you started, you ended up in CEU. So this is a little town where you cannot be lost. There is one specific prescription which way to go, and whatever your starting point was, you end up at CEU. Okay, of course, this is what happened to you. All right, so what is the mathematics behind it? This is called a finite state deterministic automaton. So it has finitely many states. So the states are the points where you have this choice. So let me number them 1, 0, 1, 2, 3, 4. So this finite states. And you have a finite alphabet. This is the word they use here. This is just left or write. So these are the instructions you give, or these are the buttons on the automaton which you push if you want to get something from your automaton. And there is some transition function. Which tells you if you are in some state and you read the instruction for the next step, then what is the next state you will be in, or the automaton will be in. So in this case, this transition function is very easy. So these are the 5 states. And one thing, so right is just going 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 0. And left is 0 to 1, 2 to 3, oops, no, 1 to 2, oh, left, 1 to 3, 2 to 3, 3 left to 4, 4 left to 1, yeah. Okay, so it's very easy to describe. So you can imagine in general, you have a finite set of states, a finite set of letters, and what you do is, and the automaton is given by this transition function, and what you do this transition step by step. So you read a sequence of letters. So what is a sequence of letters? It's a word. Like in our case, it was left, right, left, left, right, left, left. And you see what happens. And our automaton, the specific property of our automaton was that whatever place you started your trip, in the end you got to the same place, very same place, independently of your starting point. So this is called a synchronizing automaton. That means that there exists a word such that whatever is your starting state, starting from any state, it will bring the automaton into the same state, independently of the starting point. And this is what we want to study today. There are some fancy articles about synchronizing automata. You can read about crazy things that the satellite goes around the moon, and for a while you don't see the satellite, so when it appears, then you have to send some signals so that you should know in which state it is. But of course, every computer has a reset button, and it's much easier to just do this specific instruction to do that. But maybe this is, well, although it doesn't look very realistic, this little town, but still, I think it's a much better example that sometimes you can achieve this synchronization. So whatever the starting point, the end point is the same. Okay, and Cərny's conjecture, Jan Cərny, was a Slovakian computer scientist, and he formulated this conjecture in 1964, so more than 50 years ago. I have to admit I didn't read the original paper because it's in Slovakian. And some say that actually the conjecture is not formulated in that paper, but a later paper. Nevertheless, he was studying this question. And this is the problem or conjecture which is attributed to him, that for any synchronizing automaton, there is a synchronizing word. I didn't formally define that, but this is the word which sends everything into the same state of lengths. So the number of letters at most n-1 squared. This is the famous Cərny conjecture, which is open for 50 years now. Why does he conjecture this? Because it's quite easy to construct an example for the worst case when it's exactly n-1 factorial, n-1 squared, the optimal, the best, the shortest synchronizing word, namely the following automaton. So it has n states. What is n? I didn't tell, but this is the number of states. So if you have n elements, then we number them from 1 to n-1. And one of the operations, one of the alphabets, so one transformation is just a cyclic shift. So n-2 goes to n-1, and n-1 goes to 0. Okay? And the other one is also very easy. It sends 0 to 1 and fixes everything else. So let's try to prove that the shortest synchronizing word for Cərny's automaton has lengths even more precisely is b a to the n-1. That means we repeat a n-1 times b, a n-1, b, etc., a n-1 b, and the number of b's is n-1. So b, this it collapses 0 and 1. A is the cyclic shift, so you do it n-1 times. That means shifting it back one step. Again, B, collapsing, shifting back, collapsing, etc. So the length, what is the length of this? So it's 1 and n-1, so n, and I repeat it n-2 times, plus this 1, which is n squared minus 2n plus 1, and it is equal to n-1 squared, but it's a little bit misleading, so the result is not n-1 squared because it's a square, but some formula which happens to be equal to n-1 squared. Okay? So why is that so? Let's try to find the shortest synchronizing word. So first we have the whole set of n elements, and then we perform either A or B. A and B are maps, self-maps of the n-element set, transformations of the set. So you do this many, many times, and eventually everything will collapse to a single point, because the result of the composition will be a constant function. Okay, so this is the human version, which I formulated in the abstract. You don't have to worry about the specific language of automata theory, that you have states and alphabet, whatever. Actually, you have certain finite set, n-element set. You have certain self-maps, transformations of the set. And the assumption is some word. What is a word? It's a composition of these functions, self-maps, or for the algebraists, the product of the functions. There is some function which maps everything into the same state. That means it's a constant function. So the assumption is that you have some collection of functions on the n-element set such that a certain composition of these functions will give you a constant function. And the question is, what is the shortest composition, smallest number of factors, which will yield a constant function? So in each step, you do something, either A or B, and something happens. First of all, you have to notice that what matters is only the image, not actually how you got these points, how these points appeared. So there are some maps, and in each stage you are interested in the current image of the function, of the composition of the functions. At the end, you want to map everything to the single point. So in the previous, what happened in the last step, either it was a one-element image here, so it was definitely not the shortest product because you could finish already here, or some elements were collapsed. But the only way to collapse elements is this, that these two are collapsed to one. So the only possibility for the last one, if it's the optimal, the shortest product, that here you have 1 and here you had 0 and 1, etc. You build it up, the proof backwards, starting from the one element image and going backwards. Going backwards with A, it's easy because E is a permutation. You can just apply the inverse, which means shifting it back by 1. What about B? If the last step was B, then everything remains on place except that 1 could have been the image of 0 as well. So you have to add, you might have to add 0 to the current set. So the best formulation of the proof is that not exactly that you are keeping track of what is the image of the current point, but you take a large, maybe larger set, an arc, because it's a cyclic permutation. You may think of it, draw as on a circle. So you look at some stage there are some points, and you look at some arc which contains all the image points at that stage. Okay? So what happens in the previous step? The previous step, it was either A, which is a cyclic shift, so you have to shift it back 1. That's one way, one possibility. The other possibility, that you had 1 in the image, so in the arc, and then you may add 0 here. So either you shift it back, this arc will be the same length, but shifted backwards by 1. Or if 1 was here, then you either shifted back, okay, or the last map was this B, which means that 1 could be the image of either 0 or 1 or both of them. So you just add 0 here. Because 1 was there, adding 0 just enlarges this arc. If it was a shift, then it's still contained in this enlarged arc, because 1 was replaced by 0. Okay? All right, so in every step, if you move backwards, you either shift it back by 1 or you add 0, and it's possible only whenever 1 was here. Okay? So in some steps, you just shift, which means it will have the same size. So the only enlargement occurs when 1 is here and 0 is not there. And then in the previous step, you have to add that 0 to the arc. Okay? And then it's easy to see, then this is the only shortest synchronizing word. Because in every step, you have to achieve either it says the same length, no change of the length, of the size of the set, or you add this 0, but you can do it only when 1 is there and 0 is not there. So if you build it backwards, then the only way to do that is every time you do this, then you shift it back n minus 1 times, then 0, then it will be 1, 2, and then add 0, shift it back n minus 1 times, then it will be 1, 2, 3, add 0, etc. So this is the only shortest synchronizing word. Maybe it was a little too fast, but I think you grasped the idea that you have to move backwards. All right. So this is why the conjecture states that the synchronizing word we are looking for has to have length at most n minus 1 squared. It's a very simple example. It was tried for various practical, so constructing some small size automata. It was always true. Some specific sorts of automata which people study in automata theory, it was proved. But in the full generality, nothing is known which is even close to the conjectured result. So let's try to find some upper bound. Do you have some idea for some very crude upper bound, maybe? So I already pointed that what matters is just the current image of the set, of the composition of the previous maps. So it cannot happen that in the optimal situation that we have the very same set as an image in two different stages. Because this means that after applying these operations, you will get a constant. But then you can ignore the steps between and start with this, perform exactly the same things as was performed for that, and then you get the constant earlier. Okay, so all these sets must be different. Every step, you must have a different image. So altogether, there are just 2 to the n different subsets. Of course, the empty set will never occur, and If you already have a one-element set, then you stop and you don't have to worry about any further. All right, so this is a very crude upper bound, because we can do a little bit better. Namely, we just concentrate on that part of the procedure when we have a k-element subset, and for a while we have such k-element subsets, and at some stage we have something which is less than k. The first time we go below k. So that means that here we have some partial bijections between these sets. I don't know what happens with the other elements because we don't no longer see these elements. So this is just one element of the alphabet does that, another element of the alphabet does that, etc. And in the final set, there is something which maps this k-element set to some smaller set. Okay, so these two elements here have the same image. Therefore, these two elements cannot occur previously, because then I just apply this constant. Even more, if I trace back where these elements came from, then all these k-element subsets, we see these 2 points, which eventually got to these 2 points and got collapsed in the next step. So we have these k-element subsets, call them A1 prime, you will see why, A2 prime, A3 prime, AM prime. So these are k-element subsets. And the yellow ones these two-element subsets, which eventually got collapsed in the last step. And what we see here is that none of these pairs, two-element subsets, can occur inside a previous set. Because if, for example, this one was these two elements were contained in here, then I just follow take these elements from or functions from this on, and then already these will be collapsed in a fewer steps, right? So if these 2 points appear somewhere inside here, then just making these operations on that set will go from the same number of steps from here to the smaller set, right?
Maybe not to the same. Maybe not to the same.
Maybe not to the same smaller set. Yeah. So I'm now concentrating on such a part of the procedure that diminishes the size of the image from k to something smaller. Okay. So the condition is that I prime does not contain bj if I is smaller than j. Okay. Oops. Okay, before analyzing that in full detail, just maybe I wanted to make an easier observation first, sorry, but I'm so fond of this observation that I was hurrying a little bit. But okay, so this just says that what I wanted to say before going to this was that actually these pairs must be all different. That's obvious, because if the same pair occurs earlier, then by the same argument I can finish the procedure earlier. So a better upper bound is that in n choose 2 steps, we can definitely decrease the size of the image. And I have to do this n minus 1 times. So this is the cubic upper bound. So it's n times n minus 1 squared over 2. So the conjecture is quadratic, and it's quite easy to get this cubic upper bound, n cube over 2. A little improvement, but it's beautiful. So I denoted these sets by A primes because I rather want to take their complements. So AI is the complement of AI prime. So the size of AI will be n minus k. The size of Bj is 2. And if I translate this condition, what does this mean? It means that AI has a non-trivial intersection with Bj if the index of I is smaller than the index of B. And of course, AI and Bi, they are disjoint. Okay. And we have this sequence of sets. All of them has, say, A elements. Now I generalize a little bit. B elements. The theorem of Peter Frankl says that the number of sets is at most A plus B choose B. Or if you prefer more symmetrically, so it's A plus B factorial over A factorial times B factorial. Yeah. Okay, so we have a sequence of subsets of some finite set, each of the same size. Another sequence under this condition that previous A with a later J with a later B intersect, and with the same index, they are disjoint.
And the theorem is saying that the length of these sequences should be less than this?
Yeah, so the number of sets is at most this one. And the proof is wonderful. We have a finite set, and we interpret these elements as vectors in a real Euclidean space. So the points are represented by vectors in R to the A plus 1 in general position. What does this mean? Every A plus 1 vectors are linearly independent. Is it possible to find such vectors? Hmm?
Yes.
Yes. What's the clue? How to define these such vectors? Hmm?
By induction.
By induction. Okay. Okay. And directly? Hmm?
On a sphere.
Hmm?
Or on a sphere.
Or the moment curve.
Hmm?
The moment curve.
Moment curve. Yeah. Moment curve. Any points satisfy this. Okay. Okay. And now, if I take a set AI, this is a set of A elements, one less than the number of the dimension of the space. So these are linearly independent vectors. So they span an A-dimensional, a one codimensional subspace. And the easiest way to give a one codimensional subspace is to specify through a linear equation. So in geometry, yeah, so the normal vector. Vi, so which is orthogonal to this subspace. So for each set AI, we find such a vector. Now for Bj, so there are B's, we define a function on this vector space, a real valued function, the following way, that fj of a vector take the inner product of the vector with all vectors in the set Bj. Okay, so for each AI, I defined a vector. For each Bj, I defined a function of this type. What do we know about this? What is the value of fj at vi if I is less than j? Well, by our condition up there, ai and bj are not disjoint. There is a common vector. There is a vector in bj which belongs to the subspace spanned by ai. It's one of the vectors spanning that subspace. So this normal vector is orthogonal to that vector in the intersection. So one of the factors in this product is 0, so it is equal to 0. What about fi vi? Vi is a normal vector of the subspace spanned by the vectors in ai. Any ai and bi are disjoint, so if I take any b from bi, then it is linearly independent from the vectors in ai. So it's not in the subspace generated by them, so it's not orthogonal to vi. So none of these factors is equal to 0, so the product is non-zero. Okay. So that means that if I list all the f's and all the v's, the same number, m of them, both of them, then this matrix, which I get in this way, what sort of a matrix is this? So this means that this is triangular matrix, and this means that the diagonal entries are non-zeros. So what is the rank of this matrix? It's a full rank matrix, so the rank is equal to m. That means if I restrict these functions to the given set of vectors, these vi's, these are already independent on this set. So they are independent. They are linearly independent as functions. Where do these functions live? If I write this vector as a linear I choose a basis and I take the coordinates, then there are a plus 1 coordinates. Each such inner product is a homogeneous polynomial of degree 1. So if I multiply all these, I get a homogeneous polynomial of degree b. So all these functions live in the space of homogeneous polynomials of a plus 1 variables of degree b. What is the dimension of this space? Of course, a plus 1 choose b, because you just take what? B dots and A delimiters, and read this as x1, x1, x2, x2, x3, no x3, no x4, x5, etc. Okay, so the dimension of this space is a plus 1. B choose B, and there are m independent functions we found in this space, so we have this inequality. What does it mean for our problem? In our problem A, I had n minus k elements, and B 2 elements, and k starting from n going down to 2. Because each step you want to decrease by 1. Maybe you are able to decrease by more, but you cannot know it, so this is the best you can do. So it's 2 choose 2, in the next case 3 choose 2, and you go up to n choose 2, so altogether n minus 1 choose 3, so n cubed minus n over 6. So with this beautiful idea, you can still get a cubic upper bound. Only the coefficient of n cubed is not 1/2, but 1/6. Okay, so finally, my dream. My dream is not to prove Cərny's conjecture. I'm too old to do that, and I don't see any way to attack it. But this local approach that only I want to go from a k-element image to some smaller image. And all these combinatorial ideas do not actually use that we have a function on the whole set. They always just a tiny piece of the functions which are used in this. So somehow you might put them together and then shorten the way you have to go. So my dream is that from k to something smaller than k may need at most maybe constant, but n square over k steps. Why do I think this? Because in this very elementary example we started with, in the Cərny's example, you remember we had this circle, the cyclic shift, and also some very simple collapsing function. So if we have k elements on the circle, then there are definitely, by the pigeonhole principle, some which have a distance at most n over k. And then just concentrating on this pair, what I can do, I move it to that point where I can use this collapsing function, mapping 0 to 1, which can move these 2 points closer by 1. And then go around, use this again, close the gap by 1, and you have to do this n over k times, and in each step you have to go around, so it means n cyclic shifts, roughly. So in that very simple, very special case, n square over k does the job, steps does the job. And if this were true, then of course we can do n square over n plus n square over n minus 1, n square over 2, so n squared times log n would follow, so much better than a cubic bound, but still not the desired conjecture, n minus 1 squared, but it could be a great achievement. But I'm over 50, and as Hardy wrote in his book, that mathematicians over 50 never do something significant, so it's up to you to think about this problem. And also I'm a group theorist, and here this is the opposite end. Eventually you get to constant. But in the meantime, when you use this, you are not able to shrink your set, then there are always partial bijections. So I may think about what happens if these are just permutations. And the only thing I keep in mind that at the end I have to collapse something. So I have to reach these 2 points and then use this collapsing map. But up to that point, I may have only permutations. So for my group theorist mind, this is a nice question too, which may help in doing this, fulfilling my dream concerning the Cərny conjecture, that I have permutations. So permutations, elements of the symmetric group of degree n. Maybe m, r, whatever. And I have a k element set inside the n element set, and I use these some such maps, and they always give me, of course, because these are permutations, k element sets. So my goal is only that we have a target, we have 2 points which I want to push into these two into this k element set, or rather, of course, I can, because it's a group, I can talk about the inverses of the elements. So instead of moving this k element set around so that eventually the image would contain the two elements, two specified elements, I can go backwards and say, I want to put these two elements, the image of these two elements, into my original k element set. It's something like a game, like Rubik's Cube, that you move, okay, one piece is on the place, and then when you want to move the second piece, then you have to ruin what you have achieved yet already for the previous piece, because they are somehow linked together and you cannot do that. So, okay, so this is a question, group theoretic question. You have maybe not just two element set, maybe we can generalize it. So we have a element set and a B element set. We have a group generated by certain elements, subgroup of the symmetric group. And what you want to do is to find some word in this group elements, so short word, such that A, GI1, GI2, GIL is contained in B, or as it was very convenient in the theorem of Peter Frankl, rather to be disjoint. So if you take the complement, it's the same, to have it a disjoint image. And the assumption you have to use here is that, okay, so A times B must be less than N, G must be transitive, and the conjecture that A times B is the good bound for the length of the shortest word doing that. I have no time, but maybe it's a good homework to think about it, that this is necessary, otherwise we may not have any element of the group which maps A to a disjoint subset. And if you just have one cycle, then it's easy to see that A times B cannot be improved for that case. All right, so the original Cərny conjecture is an open question in automata theory. You should remember that. And maybe this nice result of Peter Frankl about combinatorial result, which is what you have to take with you home from this lecture. And if you are interested, I'm happy to discuss if you have any partial results concerning either the Cərny conjecture or my related question from group theory. Thank you very much.